Welcome to the deep dive. Today we're jumping into a really central part of organic chemistry, how chemists actually build complex ring structures. We're talking aromatic heterocycles specifically. These molecules are everywhere in medicines and materials. So our source today is chapter 30 from Clayden, Greeves, and Warren's Organic Chemistry, the second edition. It's titled Aromatic Heterocycles 2, Synthesis. And our goal here is pretty clear. Cut through all the reactions, all the mechanisms, and pull out the key ideas. How are these things actually built? We'll hit the mechanisms, the pathways, functional groups, and, crucially, that retrosynthetic thinking. Think of this as your shortcut to getting a strategy.
Exactly. And, when you first look at this chapter or just the sheer number of different heterocycles, it can seem, well, overwhelming. But the strategies underneath it all, they're often surprisingly straightforward. We'll find there are some general principles that actually make synthesizing these molecules, well, maybe not easy, but definitely logical.
Okay, so let's start there. What makes building these rings potentially simpler than expected? The book points out a few key things, right?
Right. There are basically four main advantages that work in our favor.
First is just that making carbon-oxygen, carbon-nitrogen, carbon-sulfur bonds, it's usually not the hardest part of organic synthesis. We have good ways to do that.
Absolutely. Second, intramolecular reactions. Reactions where a molecule bites its own tail to form a ring, those are almost always favored entropically. That's a huge plus for making rings.
And third, specifically forming 5- and 6-membered rings. Those are generally the easiest ring sizes to make, kinetically and thermodynamically. Less strain.
Precisely. And the fourth point is that the products we're aiming for are aromatic. They're stable. So thermodynamics is often pushing the reaction downhill towards that stable aromatic heterocycle.
So the strategy is different then compared to something like benzene chemistry.
Totally different. With benzene, you usually start with the ring and add stuff on. Here, the main game is building the ring itself, often from acyclic, non-ring starting materials. And you try to build it with most of the substituents you want already attached. Then maybe you do some fine-tuning later, perhaps some nucleophilic substitution if the ring allows it. But the core move is cyclization. Usually the heteroatom NO or S acts as a nucleophile, and it attacks a carbon electrophile, very often a carbonyl group.
So it ties back nicely to carbonyl chemistry.
Exactly. And it's all about retrosynthesis, thinking backwards. How do I break this ring apart logically?
You mentioned thermodynamics helps. Can you give an example where that really makes a difference? Maybe something that looks complicated but just works?
Sure. Think about a commercial synthesis of pyridine. You literally take acetaldehyde and ammonia, put them under pressure, heat them up. The yield is maybe only 50%, which doesn't sound amazing.
Right.
But the mechanism is incredibly complex. Lots of steps. The fact that it works at all to give you pyridine reliably, that's thermodynamics finding the lowest energy product. Or look at the synthesis of allopurinol, used for gout. Some steps look like a real witch's brew of reagents, but again, the molecules find their way.
But, while thermodynamics helps, you still need smart planning. It's not just throwing things together. The central retrosynthetic idea here is disconnect the carbon heteroatom bonds first. That usually simplifies the target molecule back to things like, say, dicarbonyl compounds and amines or alcohols. It's straight out of chapter 28 logic.
Okay, let's apply that. 5-membered rings, pair rolls first. So we disconnect the CN bond.
Yep. Disconnect both CN bonds conceptually. What does that leave you with? You need an amine source, like ammonia, and something with the 4 carbons, a 1,4-diketone.
Like hexene 2-vol-5-dione?
Perfect example. Heat hexene 2-alpha-5-dione with ammonia, and boom, you get 2-vol-5-dimethylpyrrole. High yield, very clean.
And the mechanism involves enamines. Right. The ammonia reacts with one ketone to form an elamine, which polymerizes to an enamine. That enamine nitrogen then attacks the other carbonyl group, cyclizes, and then it dehydrates to give the aromatic chirale.
Right.
It works as primary amines too, not just ammonia. That's how you make N-substituted pyroles, which you see in drugs like clopirac.
Okay, so if we swap the nitrogen for oxygen, we get furans.
Even simpler, often. Just take your 1,4-diketone and treat it with acid. The acid catalyzes the enol formation and then the dehydration steps needed for cyclization.
And this is where that control point comes in. Acid versus base.
Exactly. This is really neat. Take that same 1,4-diketone, acid, you get the furan. Add base, and the base promotes enolate formation and an intermolecular aldol reaction instead. That gives you a 5-membered carbocyclic ring, a cyclopentanone. Totally different product based on the catalyst.
Wow, okay. Can you show us a real-world example like that menthofuran you mentioned?
Sure, menthofuran, it's part of the mint smell. The synthesis is clever. Retrosynthetically comes back to a 1-mel-4 dicarbonyl type structure. One strategic move is to introduce an aldehyde group initially as an ester, which is more stable and easier to handle than reduce it later on. The key steps involve alkylating an enolate with an alpha-iodoester, then an acid-catalyzed cyclization. Interestingly, this often forms a lactone first, not directly the furan.
Lactone, okay.
Yeah, cyclic ester. Then you hydrolyze the lactone, it decarboxylates, and then you reduce the remaining ketone to an alcohol, which, under the acidic conditions, dehydrates and cyclizes to the furan. And because the furan is aromatic, it doesn't get over-reduced. Aromaticity protects it.
Makes sense. And quickly, thiophenes, the sulfur versions.
Same 1-4 ditone logic. Theoretically, H2S could work like ammonia or water, but practically, it's often easier to use reagents like phosphorus pentasulfide, P2S5, or Lawson's reagent. These essentially convert the carbonyl oxygens into sulfurs, making dicarbonyls, which then rapidly cyclize.
Right. Now, you mentioned another pyrrole synthesis, NOR, for more complex ones.
Ah, yes, the NOR-pyrrole synthesis. This is a really cunning twist, especially useful when you need pyrroles with specific, often electron-withdrawing, groups, like esters. Think components of porphyrins, like in heme. The challenge sometimes is controlling reactivity, especially at the C2 position next to the nitrogen, and handling adjacent carbonyl groups. NOR's insight was to disconnect only one CN bond differently.
How so?
It leads you back to starting materials like an alpha-amino ketone, or ester, reacting with a ketone that has an activating group, like another ester, on the adjacent carbon. The alpha-amino ketone itself is often generated in situ right in the reaction pod, typically by reducing an oxime.
So you make the oxime, reduce it to the amine, and that reacts.
Exactly. The beauty of the NOR reaction is often its efficiency. You can sometimes mix the alpha-amino ester, or the precursor oxime, and a reducing agent like zinc, with the activated ketone, or ketoester, add some acid, and it all happens in one pot. The amine forms an imine with one carbonyl, and that enamine cyclizes onto the other activated carbonyl group. It's a classic name reaction for a reason very powerful.
Okay, that covers 5-membered rings pretty well. Let's expand now to 6-membered heterocycles. Pyridines, for instance. Same logic apply. 1-theraphyl-5 dicarbonyls this time.
Pretty much. The core idea holds. Use a 1-therol-5 dicarbonyl compound and react it with ammonia or a primary amine. The main difference is that the initial cyclization product is usually a dihydropyridine. It's not aromatic yet.
So you need an extra step.
Yeah, you typically need a final oxidation step to get to the fully aromatic pyridine ring. Sometimes this happens spontaneously with air, but often you add an oxidizing agent.
That brings us to maybe the most famous pyridine synthesis, the Hansch synthesis. It sounds complex, 4 components reacting.
It is complex, but also really elegant in how it brings everything together. It involves an aldehyde, ammonia, and 2 equivalents of a beta-keto ester.
Okay, break that down. How does it likely work?
Well, the proposed mechanism likely involves a couple of things happening at once. First, you probably get an aldol condensation between one molecule of the keto ester and the aldehyde, followed by dehydration to form an alpha-beta unsaturated ketone. That's a good Michael acceptor.
Right, susceptible to nucleophilic attack.
Exactly. Then a second molecule of the keto ester likely forms an enamine with the ammonia. This enamine then acts as a nucleophile and undergoes a Michael addition to the enone we just formed.
Ah, connecting the pieces.
Yep. Then there's an intramolecular cyclization. The amino group attacks the remaining ketone carbonyl, and after dehydration, you get the dihydropyridine ring. Like we said, usually needs that final oxidation step.
It's amazing that works so well. And these Hansch products, especially the dihydropyridines, before oxidation, they're actually really important drugs, aren't they?
Hugely important. They are the basis for a major class of calcium channel blockers used to treat heart disease angina, high blood pressure. Drugs like nifedipine, philodipine, amlodipine, they are all based on that Hansch dihydropyridine core.
And if you need an unsymmetrical drug where the 2 keto ester-derived parts are different.
And you have to be more strategic. You can't just mix everything together. Usually you'd preform 1/2 the molecule, maybe the ene part, and then react that with the enamine part in a separate step. It's called the Novonagel-Hansch approach.
Are there other ways to make pyridines?
Oh, sure. You can sometimes use hydroxylamine instead of ammonia, which can sometimes avoid the need for that final oxidation step. And building the required 135 decarbonyl precursors often involves using standard tools like the Mannich reaction or Michael additions. Lots of ways to get there.
Okay, what about pyridones? They look like pyridines, but with a carbonyl in the ring.
Right. Pyridones, or more accurately, pyridine 2,1s. Their synthesis often uses a 1,2,3 dicarbonyl compound and something that provides the CNC unit. A common partner is cyanocetamide.
Cyanocetamide. Okay, how does that come together?
You can often make the precursor you need, which is essentially a ketoaldehyde or a derivative, using a Claisen condensation. Then, remarkably, you can often just mix the enolate of that precursor with cyanocetamide in one pot. It involves a cascade. Proton transfer, the enolate attacks the nitrile of the cyanoacetamide. Cyclization occurs as the amast nitrogen attacks a carbonyl, followed by dehydration. It's another efficient, multi-step, one-pot process.
Let's switch gears slightly. Rings with two heteroatoms, usually nitrogen. Pyrazoles, how are they made?
Pyrazoles come from reacting 1,4,3 dicarbonyl compounds with hydrazine. Hydrazine is H2N and H2. Because you have two nitrogens in the region, you form the five-membered ring with two adjacent nitrogens directly. And conveniently, it usually forms the aromatic ring straight away, no oxidation needed.
And this chemistry is used in some very well-known drugs.
Absolutely. The synthesis of sildenafil Viagra is a fantastic example. It features a pyrazole ring fused to a pyrimidine ring.
So how does the pyrazole part get made there?
Retrosynthetically, the core structure comes back to a functionalized 1,000 3-count-5 tricarbonyl compound, a diketoester. You can build that precursor using, guess what? A Claisen condensation. Now, the tricky part is reacting it with hydrazine. If you use simple methylhydrazine, you'd have a regioselectivity problem, which nitrogen attacks which carbonyl.
Ah, right. Two different nitrogens, two different carbonyls.
Exactly. So the chemists cleverly solved this. They first react the diketoester with symmetrical hydrazine, H2 and NH2, to form the pyrazole cleanly. Then they selectively alkylate the pyrazole nitrogen they want using dimethyl sulfate. Very neat control.
And after that?
Then there are several more steps. Nitration of the attached phenyl ring, conversion of an ester to an amide, reduction of the nitro group to an amine, and finally building the fused pyrimidine ring. But the pyrazole formation is key.
Just briefly, what about other dinitrogen rings, pyridazines and pyrimidines?
Sure, pyridazines have the two nitrogens next to each other like pyrazoles, but in a six-membered ring. They come from 1-4 diketones plus hydrazine, but like pyridines, they usually need an oxidation step. Pyrimidines have the nitrogens in a 1-3 relationship in the six-membered ring. They typically come from 1-3 dicarbonyls reacting with amidines compounds with a CNH, NH2 sort of structure. Trimethoprim synthesis is a good example there.
Okay, this issue of regioselectivity seems really important, especially when you have unsymmetrical reagents. Let's dig into that. Thiazoles are a good case study.
Definitely. Thiazoles have both a nitrogen and a sulfur in a five-membered ring. A very common and effective way to make them is the Hansch-thiazole synthesis, similar name, different ring, reacting an alpha-haloketone with a thiamide.
Alpha-haloketone and a thiamide. So multiple reactive sites again. How does it know where to react?
This is a beautiful illustration of hard-soft acid-base theory, HSAB. Think about the electrophiles. You have the hard carbonyl carbon and the softer carbon attached to the halogen, and the nucleophiles and the thiamide, the hard nitrogen and the softer sulfur.
Hard reacts with hard, soft reacts with soft.
Pretty much. The hard electrophile, ketone, reacts preferentially with the hard nucleophile, nitrogen. The soft electrophile, alkyl halide carbon, reacts preferentially with the soft nucleophile, sulfur. This pairing directs the bonds to form correctly, giving you the thiazole regioselectively. The synthesis of the anti-inflammatory drug Vineazac uses exactly this principle.
That's a really useful concept. Okay, moving to isoxazoles, nitrogen and oxygen next to each other in a five-membered ring, what are the routes here?
Two main ways. One is similar to pyrazole synthesis, react to 1-3 diketone, but this time with hydroxylamine, H2NOH, instead of hydrazine.
And regioselectivity issues here too, with unsymmetrical diketones.
Yes. Which oxygen or nitrogen ends up where depends on factors like pH, which affects the nucleophilicity of the N versus the O in hydroxylamine, and also which carbonyl in the diketone is inherently more reactive. An aldehyde carbonyl is usually hotter than a ketone carbonyl, for instance. So you can sometimes control it.
And the second route for isoxazoles?
That's using 1-3 dipolar cycloadditions. This is a different class of reaction altogether. You generate a reactive intermediate called a nitrile oxide, which has this sort of N-positive negative charge separation. This dipole then reacts with the dipolarophile, typically an alkyne, in a concerted cycloaddition reaction to form the isoxazole ring directly.
Dipolar cycloadditions. Sounds powerful. Any challenges?
Regioselectivity can sometimes be an issue, deciding which end of the dipole adds to which end of the alkyne. Also, nitrile oxides themselves can be unstable. They can dimerize if you don't have the alkyne present. But where this really shines is in intramolecular versions. If the nitrile oxide and the alkyne are part of the same molecule, they're forced to react together, often with very high selectivity.
These cycloadditions work for other heterocycles too. Tetrazoles, triazoles.
Absolutely. Tetrazoles with 4 nitrogens can be made by reacting nitriles with the azide ion, N3. You have to be careful, though. Using hydrozoic acid, HN3 itself, is dangerous. It's explosive. Sodium azide is usually preferred. Tetrazoles pop up in drugs as replacements for carboxylic acids, like in some indomethacin analogs or the drug Carbonyl.
And triazoles, 3 nitrogens, azides again.
Yes, triazoles are typically formed from reacting azides with alkynes. Now, just heating them together often works, but you usually get a mixture of regioisomers, the 1,4 and the 1,5 substituted triazoles.
Ah, but this is where click chemistry comes in.
Exactly. This is where Barry Sharpless's Nobel Prize-winning work made a huge impact. Adding a copper catalyst dramatically speeds up the azide alkyne cycle addition and crucially makes it highly regioselective. You get almost exclusively the 1-vol isomer.
And it works in water.
Yes, which is incredible. Fast, clean, highly selective, often works in water. That's why it's called click chemistry. The components just click together perfectly. It revolutionized how people make triazoles and use them, especially in biological chemistry and material science.
Okay, let's shift to a real heavyweight, a reaction that gets its own section in many textbooks. The Fischer-Inbol synthesis. Why is this one so important?
It's arguably the most important method for making indoles, which are incredibly common structures in natural products and pharmaceuticals. Think serotonin, tryptophan. Emil Fischer developed it back in the 1880s, and it's just a masterpiece of mechanistic complexity working reliably.
So walk us through that mechanism. It sounds intricate.
It is, but it flows logically. Step 1, you react phenylhydrazine, or a substituted version, with an aldehyde or ketone. This just forms a phenylhydrazone, which is basically an enamine. Standard reaction.
Okay, formation of the hydrazone. Got it.
Step 2, the hydrazone tautomerizes to its enamine form. Remember, enamines can do that if there's an alpha proton. So now you have a CCC double bond and an NN single bond.
Enamine formation. Check.
Step 3. This is the crucial named step, a 3-3 sigmatropic rearrangement. It's like a Cope or Claisen rearrangement. Electrons shift around a 6-membered ring formed transiently by the atoms of the enamine and the benzene ring. The net result is breaking the weak NN bond and forming a strong CC bond between the benzene ring and the former enamine carbon.
Wow, okay. A sigmatropic rearrangement, that forms the key CC bond.
Exactly. Step 4. The molecule wants to get its benzene ring aromaticity back. So proton shifts and the benzene ring re-aromatizes. This leaves you with an intermediate that has 2 nitrogen atoms attached to the same carbon and an aromatic amine elsewhere.
Almost there.
Step 5. The aromatic imine nitrogen now attacks the imine-like carbon intermolecularly, forming a 5-membered ring containing an aminal, a carbon bonded to 2 nitrogens.
An aminal.
Final step, step 6. Under the acidic conditions, the reaction is usually acid catalyzed. The aminal breaks down. It kicks out ammonia, or anemone if you started with a substituted hydrazine. A double bond forms, and voila, you have your aromatic indole ring.
That's quite a sequence, forming the hydrazone, tautomerizing, the 3-3 shift, re-aromatizing, cyclizing to an aminal, then kicking out ammonia. Amazing, it works so smoothly.
It really is. And controlling regioselectivity. Often, it's built in. If your ketone can only form an enamine on one side, the reaction goes one way. Or if your phenylhydrazine only has one free ortho position on the benzene ring, the CC bond can only form there. Symmetrical starting materials also simplify things, of course.
Can we see how this plays out in some real drug syntheses?
Absolutely. Sumatriptan, the migraine drug, the synthesis uses the Fischer reaction. They often protect the aldehyde they need as an acetyl first. Polyphosphoric acid, PPA, is a common strong acid catalyst for this reaction. Later, they add the side chain involving steps like reducing a nitrile and then reductive amination. The Eschweiler-Clark methylation is a classic way to get that dimethylamino group on.
Okay, another one.
Ondansetron, the anti-nausea drug. It also uses a Fischer-Indole synthesis. Here, they often use a Lewis acid like zinc chloride as the catalyst. The specific diketone they start with is designed so that the enamine formation naturally occurs at the position needed to give the final fused ring system correctly.
And indomethacin, the anti-inflammatory.
Another classic Fischer-Indole example. Here, the regioselectivity of enolization under the acid conditions directs where the CC bond forms. They also use tert-butyl esters sometimes as protecting groups because they're easily removed later under acidic conditions that don't mess up the indole.
It's clear the Fischer-Indole is powerful. Are there alternatives if it doesn't give the pattern you need?
Yes, for instance, the Racert-Indole synthesis. It proceeds through a different mechanism and often favors substitution patterns on the benzene ring that are different from what the Fischer synthesis typically delivers. So chemists have options depending on the target molecule.
Let's move to fused ring systems now, specifically quinolines and isoquinolines. Quinolines are the core of quinine, the antimalarial, and quinolones are crucial antibiotics like pofloxacin. How are these built?
For quinolines, the basic disconnection strategy involves breaking a CN bond to the pyridine part and a CC bond connecting it to the benzene ring. This suggests you need an aniline derivative, the benzene part with the nitrogen, and some kind of 3-carbon unit, ideally equivalent to a 143 dicarbonyl, though using simple things like malonic dialdehyde itself is often tricky.
And this leads to the Scraup reaction, which sounds a bit notorious.
Yes. The traditional Scraup reaction was pretty notorious. You take your aniline, throw in concentrated sulfuric acid, glycerol, which dehydrates in the hot acid to make acrylane, the actual C3 unit, and often an oxidant like nitrobenzene or arctic acid. Then you'd heat it vigorously. It could be quite energetic. Definitely not pleasant.
Sounds like something you wouldn't want to do on a large scale today.
Not really. Thankfully, modern variations are much more civilized. Often you'll preform the Michael adduct between the aniline and acroline, or a similar alpha-beta unsaturated carbonyl. Then you cyclize this intermediate under controlled acidic conditions, and finally use a milder oxidant like maybe DDQ or even just air to get the aromatic quinoline.
Can you control regioselectivity if the aniline has other groups?
Yes, often by choosing the starting aniline carefully. For example, to make 8-quinolinol, also called oxine, you'd start with orthoaminophenol. The hydroxyl group directs the cyclization, and there's only one free ortho position for the ring closure to happen.
Okay, and quinolones, the ones with the carboxylic acid group, like in antibiotics.
Right, the 4 quinolones usually have that acid group at position 3. A common route starts with an aniline reacting with an enol ether derived from diethyl malonate, like diethyl ethoxymethylaminate, EMME. This builds the key skeleton. Cyclization is then usually achieved by heating, often thermally, or sometimes with acid catalysis. A more complex example, like the antibiotic rosoxacin, shows how you can build these systems in stages. You might construct a pyridine ring first, maybe using a modified Hunt synthesis, and then use that functionalized pyridine as part of the aniline component to build the crinoline ring onto it. The final cyclization step's regiochemistry can be really critical and sometimes dictated by steric hindrance.
And like pyridones, these quinolones can be modified.
Yes, the carbonyl group can be converted to a chlorine using reagents like phosphorus oxychloride, POCl3. That chloroquinolines is then activated for nucleophilic aromatic substitution, allowing chemists to introduce various groups, which is super important for tuning antibiotic properties.
And isoquinolines, where the nitrogen is in a different position relative to the fusion.
Isoquinolines are isomers of quinolines. A common synthesis is the Bischler-Napieralski reaction, which involves cyclizing a beta-phenylethylamide using dehydrating agents like PPA or POCl3 to form a dihydroisoquinoline, followed by oxidation to the aromatic isoquinoline. Another route uses an intramolecular Vilsmeier reaction, generating a reactive aminium species to drive the cyclization.
We've covered a lot of ground, from simple 5- and 6-membered rings to these fused systems. Do these principles extend even further to more complex fused heterocycles found in drugs?
Absolutely. Take something like an imidazopyridazine, found in some modern drugs. The synthesis will likely involve steps we've seen, maybe forming one ring first, then using functional groups on that ring to build the second one via nucleophilic attack or cyclization, or look at the thiazole ring in timolol, the beta blocker. Its synthesis will rely on reactions forming CN and CS bonds, likely involving regions like thiamides or thireas reacting with appropriately functionalized partners, applying principles like we saw for thiazoles. The core toolkit remains the same.
So to sort of wrap up the synthetic strategies, the book summarizes 3 main approaches.
That's right. It's a good way to think about it. First, there's ring construction using ionic reactions. This is the most common theme we saw. Heteroatoms acting as nucleophiles, attacking carbon electrophiles. Think 1,4 dicarbonyls giving pyrols, furans, thiophenes, or 1,3 dicarbonyls giving pyrazoles and isoxazoles, or alpha haloketones giving thiazoles and imidazoles. It's the workhorse method.
Okay, ionic reactions. What's the second major strategy?
The second is ring construction by cycloadditions. We saw this with the 1,3 dipolar cycloadditions for making isoxazoles, triazoles via click chemistry, and tetrazoles. And crucially, this category also includes paracyclic reactions, especially sigmatropic rearrangements. The absolute star here is the Fischer-Indol synthesis with its 3,203 sigmatropic rearrangement.
Ionic reactions, cycloadditions. And the third?
The third strategy is modification of existing heterocyclic rings. Once you have a basic heterocycle, you can functionalize it further. For electron-rich rings like pyrrole, furan, thiophene, and indole, Electrophilic aromatic substitution is common, similar to benzene but often much more reactive. For electron-poor rings like pyridine and quinoline, nucleophilic aromatic substitution becomes important, especially if there are leaving groups present or activating groups. We also saw how pyridones and quinolones can undergo reactions. And finally, you can use methods like lithiation next to the heteroatom, followed by quenching with an electrophile for very precise substitution.
It's a really comprehensive toolkit. This deep dive shows just how much strategic thinking goes into building even molecules that look simple on paper.
It really does. The ingenuity involved in figuring out these pathways, controlling selectivity, and making reactions efficient is, well, it's what makes organic synthesis so challenging and rewarding.
So, maybe a final thought for everyone listening. When you see a complex drug molecule with multiple heterocyclic rings, think about how understanding these fundamental principles, ionic reactions, cycloadditions, modifications, allows chemists to not just make that molecule, but to actually design a way to make it efficiently from simple starting blocks. It's about turning these complex chemical puzzles into elegant, practical solutions.
Exactly. And these aren't just historical reactions. Chemists use these principles every single day to tackle new synthetic challenges, adapt methods for different targets, and ultimately create the molecules that shape our world, from medicines to materials.
Well, thank you for joining us on this deep dive into Chapter 30 of Clayden, Greaves, and Warren, focusing on the synthesis of aromatic heterocycles. We certainly hope you feel a bit more grounded in these core strategies and maybe even inspired by the elegance of organic chemistry. Thank you for being part of the Last Minute Lecture family.